So, hi everyone. Thank you for joining my talk today. And yeah, as you can see on the slides, I'm going to spend the next 50 minutes talking about creative coding in Rust, and in particular about writing a simple generative music application using one of the creative coding frameworks available in Rust called Nannou. And before we dive in, I would like to give just a brief outline of the topics I'm going to be covering today. First, I will give a brief introduction of my own professional background, and then give a bit of a definition on what creative coding itself is. Then I will dive into more technical topics. Why is Rust a good choice for creative coding? And in particular, why is the Nannou framework really well suited for that? After that, I will give a bit of an introduction into what a Nannou application looks like in terms of the overall code structure. And finally, we will get to the part of building the actual application. First, I will show a few diagrams of the overall structure of it, so you better understand the code. But then I will switch over into VS Code, and we will get to dive a little bit deeper. And at the end, I will give a few links to interesting resources where you could learn more about this topic. So first, a little bit about me. I have taken a bit of a side entrance into the world of music tech, as you can see. Originally, I graduated as an electrical engineer, but pretty much immediately shifted into software development. And for the first 8 years of my career, I've been developing finance and healthcare applications, writing mostly backend and application code. And all of this in JVM-based languages, with Java and Scala being the most important ones of them. In 2015, when I moved to Berlin, I joined SoundCloud, initially as a backend engineer, again, writing Scala code, but then quite quickly I shifted into more of a managerial position, and I've been doing that for a couple of years. And in 2018, I joined Native Instruments, again, in a leadership job, but the way things are set up at Native is that engineering managers were very much hands-off when it comes to the technical work and focusing on people management only. Therefore, I couldn't really scratch the coding itch in that job. So I've decided to take a bit of a break from management, and in the last couple of months, I've been using my time to get back into coding, and Rust was one of the first languages that came my way that looked very interesting. And of course, throughout all of this, I was an amateur musician and music producer, which I'm sure is something that a lot of you in the audience can also relate to. So, creative coding. It seems like a great way to combine my interest for music and for coding. And you can see an example of a creative coding project here on the screen. So this animation was actually done using the Nannou framework. And the artist is called Alexis Andre. He has a really great Instagram account. If you're into trippy visuals, I highly recommend that you follow him. He does one of these every day, and they're all pretty amazing. But beyond just cool-looking animations, what is creative coding? So this is an attempt at an informal definition. Creative coding is the act of writing computer programs in order to create something that is expressive rather than purely functional. So works of art, music, design, architecture, or even fashion. So animations are nice, but you can also use creative coding frameworks to control lights via the DMX protocol on a big stage, or you can control lasers. Nannou is particularly good at that. Or you can generate music with it, you can generate MIDI information with it. Really, the possibilities are quite endless. But why do it in Rust? One of the main things that stood out to me when I started to play around with Rust and learn it is the really great developer experience. There's a standard built-in package manager, which does a pretty good job at managing the dependencies, compiling the code, making distributable binaries, and so on. And it's also really well integrated into the rest of the toolchain, well documented, so overall, pretty good experience. Also, the Rust compiler produces actually helpful error messages, which has not been my experience in some other programming languages. So in Rust, you do get a very clear description of what the error is, and in some cases, it even provides a suggestion for how you might want to fix it. So pretty good, again, for a beginner. And there's also really great documentation available online. There's the official Rust documentation, there's the official Rust book, freely available, and a lot of effort was put into making it as beginner-friendly and as high quality as they possibly could. And finally, Rust has a very kind and welcoming online community, which as a beginner, I really appreciated. Whenever I needed to ask questions, there was a relatively quick and helpful answer. But of course, this is an audio conference, so performance is one of the key aspects, and I'm not going to go into the specifics here because, of course, benchmarking and performance are very deep topics, but overall, the conclusion seems to be that it is on par with C++ for many use cases, and I've linked to the benchmark that seems to be the most cited online, and the details are in there, basically on par, some cases slightly better, some cases slightly worse. Safety is one of the selling points of Rust, and there are a couple of design choices that went into making that happen. The first one is that all variables in Rust are immutable by default unless you declare them to be mutable. This is not really ensuring safety, it's more about helping you be more conscious of deciding whether this bit of data should be mutable or not. So it's more for the programmer to make those choices. But there are some design features for memory safety. For example, there is no such thing as a null pointer. If you want to indicate that something may or may not be present, then there's the option type available. And this forces you to actually explicitly unwrap this option in your code and decide what to do if it's a none value or if there is an actual value in there. Also, there's different types of pointers. There are immutable pointers, which you can have multiple of, or you can have a single unique mutable pointer. Again, very helpful for avoiding data races or a whole class of bugs that might come from that. And finally, the Rust community likes to use this phrase, fearless concurrency, which means that there are some really nice abstractions, even beyond the mutexes and similar concepts that you might be used to from the C++ world. And we'll be using one of these abstractions in the code. So why choose Nannou as the creative coding framework? One of the main things that the designers and makers of Nannou set out to do was to create an open source ecosystem of related libraries that can be used together really nicely. And they like to call this batteries included. So in other words, whatever your creative project is, whether you're doing 3D graphics or controlling lights or generating MIDI, generating audio, there is a library available that you can use quite easily. So as you can see, here's a couple on the screen. Support for windowing and events, support for UI widgets, 2D, 3D graphics, and a variety of protocols. So starting from more common things like OSC or DMX for controlling lights, serial communication, MIDI, of course, all the way to something a bit more exotic, which is the Ether Dream laser communication protocol. So you can see there's plenty of integration possibilities as well. And speaking of libraries, the Nannou framework has decided to prefer to drive forward the implementation of sometimes less mature Rust libraries depending on C bindings. And they've done that for two reasons: provide an easier onboarding experience for people using the framework, and also make it easier for people to contribute to the code base. So in both of these cases, there's no need to learn an additional programming language or set up a more sophisticated toolchain. Building and running is still all done using Cargo, and potential contributors don't need to learn C in order to contribute upstream. Now, let's see what a Nannou application looks like. This here is the minimum viable Nannou app. This compiles, this runs, it doesn't do anything terribly exciting. It opens the window. But I think it's a good way to start familiarizing ourselves with the overall structure of things. So people who know the model view controller pattern might recognize that we have the model view and event functions, which correspond to the model view and controller part of the pattern. And the main function itself basically initializes the app, registers the event handler function, and opens up a window and runs the app. Pretty straightforward. If you want it even more straightforward, there's also the option to create something that Nannou calls a sketch, which is extremely simple. All it does is provide you a view function, and this is where you would draw things onto the screen, or into the window, rather. Just a brief comparison of these two different approaches. So in a sketch, you can get started drawing immediately. In an app, you need a bit more setup, but as you've seen, also not that much more complicated. Sketches don't allow for models. In other words, you cannot really maintain an internal state of your app. It's pretty much a one-off. You draw something on the screen, and that's the extent of it. Also, sketches don't support the more advanced functionalities that you get from additional libraries like audio or MIDI communication or lasers or anything of that nature. We've already seen that the main function of a sketch and an app looks slightly different, but one thing they do share is you can do some pretty awesome stuff with either one of them. So speaking of awesome stuff, let's build a simple generative music app. First, just a little bit about the scope itself. What we're going to build is a standalone music application, a standalone desktop application rather, with an interactive UI, which will play MIDI notes, so it's not directly making any sound. And the overall design and philosophy of it was very much inspired by generative modular synth patches. So anybody who's familiar with that approach will definitely see some similarities. And since our app is not making any sound, I'm going to use a standalone virtual instrument called Decent Sampler and load a nice piano library into it. So both the sampler and the library are available from the URLs above. And actually, the piano book community is a really great place for high-quality sample packs. And all of them are community-made and contributed. So even beyond the scope of this talk, I recommend that you check it out. I will do this in 2 stages, just to introduce the overall structure first, and then we'll take it to the next level and make it a little bit less repetitive and a little bit more musical. So in step 1, we're going to have a sequencer object which gets the pitch information from the boxes drawn above. So a pitch generator that is run through a quantizer just to constrain our random melody into a musical scale to make it a little bit more pleasing. And our sequencer also talks to a trigger generator, which will emit triggers with a certain probability. Initially, this will be set to 1, so there will be a trigger on each clock tick. There's also a feature to play and pause the sequencer, and of course, to emit the actual MIDI notes via the MIDI out. Step 2 things get just a little bit more complex, but it does pay off when we listen to the results. So here, again, we get the pitch information from the boxes represented on the top. I've added a second pitch generator and also an adder. And what this allows us to do is to have one of the generators play a melody, and then that melody be transposed using the output of the second generator. On the bottom here, we have an additional box called a clock divider. Again, it's a very simple module. All it does is that it only lets the clock pulses pass that are multiples of the division factor that you've set. And all of these parameters will be available to control by the user interface. And let's see the code itself. All right, so step one. Actually, I'm going to run it first so we can see and hear what we get. Whoops. So as you see on the bottom there, we're just logging all the notes that are being played, and we can play and pause either by hitting the spacebar or clicking the button here. If I keep playing and adjust this scale selector up here, we can switch into minor scale or even minor pentatonic. These are just a few examples that I've included, but of course you can make your custom scales whatever you like. We can also decrease the probability of a trigger happening. So if I set it to somewhere here, now we will only get a trigger 63% of the time. Again, this is very much inspired by how the generative music patches happen in the modular world. And putting it back to 100 again, we get a note on every trigger. Great, so how is this actually made? I will actually start by opening up the sequencer.rs file and explain the internals of it a little bit, and then we get to the UI part. So here we have the sequencer. It's a relatively simple struct. It only has two things, a sender and a timer. And both of these are really crucial for implementing the functionality that we have here. So how are they initialized? That happens in the new function here. And this is the point where we introduce one of these neat abstractions that Rust provides for asynchronous communication between threads. This is called a channel. And when you create a channel, you get a sender and a receiver. In our case, we're going to use the sender in this sequencer object. And this will be running on the UI thread. In other words, whenever we change something on the UI, it will be submitted into the sender. The receiver will be passed on to the sequencer thread, and it will be used to actually receive these updates on the other thread that's taking away on the background and playing the MIDI notes, and then apply whatever changes were requested. So we initialize that here. We initialize our sequencer thread, and we start a timer, which is a repeating timer. Right now it's just a set duration. It repeats every 300 milliseconds. Okay, so we have initialized our sequencer. We've created a sequencer thread. We started running it, but nothing happens yet until we actually initialize the MIDI output here in the sequencer thread, new function. I will spare you the details. All it does is make some simplifying assumptions about which MIDI port I want to use. Basically, I'm going to take the first one that's available, which on my setup right now is the IAC bus 1. And this is how we're connected to the instrument running in the background. So we're doing some setup here and construct our thread. We're done. The next important feature is what happens when the clock is ticking. First of all, in the sequencer thread, we are trying to look at all of the messages that were not processed yet. In other words, or the messages that might have come in between the previous 300 millisecond repetition, and do a pattern match on these commands to figure out what needs to be done. If it's a start command, we start playing. If it's a stop command, we stop. And there are two commands which allow us to reconfigure the generators that are running inside of the thread to produce a different output. So once we've processed our incoming commands, it's time to play a note, but only if the sequencer is playing. If it is playing, then we call the pitch generator. We also call the trigger generator. And if there is a trigger happening on this clock, for example, if our random generator has decided not to emit a trigger, then we're not going to hear a note being played. But if we do have a trigger, then we convert the pitch into a MIDI note, emit a note on message, wait a little bit, emit a note off message, and we're done. So relatively straightforward. And one thing of the puzzle that is still missing is how do we control the pitch generator and trigger generator? We're doing this right here. So this is all inside of the sequencer. We have the public functions to update pitch generator and update trigger generator. These get updates from the UI, which I will show you shortly, and wrap those up into the appropriate sequencer command and send it over via this asynchronous communication channel. All right, so how do we actually control things and how do we build up the UI? So this is the main.rs file. This is where our application is initialized. On the top, we have a couple of constants for default values. Not terribly interesting, but definitely useful for initializing our UI with some meaningful values. The main function is where I initialize a logger just for debugging purposes and where we run the app. Our model is what represents the internal state. So we have a couple of fields here which are related to the user interface and the widgets. These are pretty much required if you want to use the widget library. But starting here, we have our own internal model and our own internal state. So we have a sequencer instance. We also have a sequencer model, which is just a smaller struct to encapsulate the parameters that we want to pass to the sequencer. In our case, this is trigger probability, which was controlled by the slider on the right, and the quantizer scale, which was controlled by the drop-down list on the left. So we implement the model function here. This is called once when the application is initialized, and we are expected to return an instance of our model. So we're doing exactly that. We're creating a window. We're setting up the UI itself for rendering. We generate unique identifiers here. So all of this is pretty much boilerplate that is required to start building a UI in Nannou. Where the interesting stuff comes in is when we start building the sequencer model, again, initializing it with default values, which are constants defined at the top, and constructing our sequencer using that model, and then returning the full model itself, which includes the fields related to the UI, but also the fields related to our own application logic. The keyPaste function here is actually registered as a callback over here. And what this allows us to do is react to key presses in a very straightforward way. As you can see, the key is passed in here whenever a key is pressed. And we do a pattern match. Again, just toggle the sequencer playback depending on the current state, whether it's playing or not. A little bit further down, we're making use of a macro that comes with Nannou called widget IDs. And just as a side note, macros are not as scary and dangerous in Rust. They are actually used quite extensively, and they're relatively beginner-friendly as well. And the implementers of Nannou have chosen to create macros to help us do some of the boilerplate stuff of setting up a Nannou UI. And here we have the update function. This one is called every time the user interface is redrawn. So this is where we're going to define the layout. We're going to create 2 rows, as you've seen, the really small one at the top, and there was a bigger one at the bottom with the play pause button. And the canvas actually allows for a responsive UI. So if I just start the app again, really briefly to demonstrate that, maybe it will be helpful. Yeah, we don't need to play anything, just demonstrate that by setting up this structure of canvases, so the 2 rows and 2 columns in the first row, we're able to have a user interface that's reactive and resizable, which is pretty neat. So coming back to the code again, this is the part where we set up the structure. We have the canvases, as I described. We're setting colors on them, borders on them, pretty standard UI code. And here we start by creating the drop-down list that is used for selecting the scale. Again, there's a lot of boilerplate stuff that I won't go into, but the general idea for creating widgets in Nannou is you call the new function, you pass in either the items that are available in a drop-down list or minimum and maximum values for a slider or the initial state of a toggle, like the play pause toggle that we had. And then we use this builder pattern where we just keep calling functions to set the different parameters of our widget, including color, size, padding, and so on. And the trick to make the widget resize as the window is resized is by putting it in the middle of the canvas that we defined above in the whole hierarchy of canvases, and also to define the width and height of this widget to be the same as the canvas that it's living in, with a padding of 5 pixels. And finally, we set a unique identifier for this widget, again, in order to be able to use it with the general Nannou UI framework. In this code block here, we can handle value changes on our widget. So in our example here, this is a drop-down list. So this code block gets called whenever a new value is selected in the drop-down. So we do some logging, again, for keeping track of things. And most importantly, we are calling the update pitch generator function on our sequencer, which in turn will take this new configuration, basically the new scale that we selected in this case, and pass it on to the sequencer thread, which will then receive it via the communication channel and apply it on the next clock tick. Next one here is the trigger probability slider. As I already explained, it's a very simple and very similar process of creating the widget, setting its properties, and defining a code block here which allows us to react to changes in the values. Up here, we do a little trick by just rounding it to 2 decimal places, because I didn't want to deal with the full precision of a float 32. And if the value is different from the previous value that we had in the model, then we update the value to the slider's new value and pass it on again to the sequencer thread where it will be applied on the next clock tick. And finally, we have the play pause toggle. I will spare you the details of all of that above. And the code block here does pretty much the same thing that the key press function did, which is toggle the playback state. And finally here at the end, we have a very simple view function. This is, again, boilerplate that is required to draw our widgets onto the window. So overall, pretty straightforward stuff. Now, we've been talking about trigger generators and pitch generators, which are defined in this module.ros file. Again, a couple of constants up here to define the different scales that we can use, and some additional utility functions. This is the first one that's interesting. So I've defined a trigger enum to indicate whether a trigger is on or off on a given clock tick. And I've also defined a trait, which is similar to an interface in other languages, called trigger module, which defines a function called tick. And the only argument here is self, so the object itself that it's called on. So in other words, this will be a method as opposed to just a free-floating function. And we're expected to return a trigger enum. The only implementation of this trigger module right now is the random trigger generator, which is defined here. When we construct it, we pass in a probability, which will be the value of the slider on the top right, as you've already seen. And we initialize a random number generator. And down here is the implementation of the trigger module trait. And all we do is generate a Boolean using our random number generator with the probability that was passed in, and then convert that from a Boolean into a trigger enum and return it. So this takes care of the triggering. Now, what about the pitches? We have a couple of different pitch generator types. The one currently used in this example is the random one, so I will only cover that. Pitch module trait, there it is. Again, very similar to the trigger module trait, we define a single method here, but instead of a trigger, we return this letter octave, which is defined in a library called pitchcalc. It's a very convenient way to represent musical notes using their letter name and a number to indicate which octave they're in. So it's pretty neat that this exists. And again, this is within the same ecosystem of libraries. And a random pitch generator itself is initialized using a minimum and maximum note that we're expecting. And on every clock tick, we generate a random value within that range, convert it to a letter octave instance, and return that. Next up is the pitch quantizer. This is the module that takes any incoming letter octave, so a musical note, and constrains that to a predefined musical scale. This one is initialized with a vector of the notes that we're allowing. This is only a letter part of the letter octave, because we don't really care about which octave it's in, as long as it's a C, whichever octave it is, and it's enabled, then the note will pass through the quantizer unchanged. We also pass in an input. So this is similar to plug in the pitch generator module into the quantizer in your modular system. So the output of a sequencer or an LFO goes into your quantizer, and the quantizer is configured with which nodes it allows, and then passes it on through its own output. So on every clock tick, our quantizer is actually going to call the tick function of the pitch source that it's connected to on its input side, and do some wrangling here to quantize up to the next enabled node. So that's all there is to it. This is version 1 with relatively simple controls and, yeah, somewhat repetitive results. Now, step 2 is where things get interesting. First of all, you will notice that our main.rs file has grown significantly, but before we dive into the code, let's see and hear what it does. So, a lot more user interface widgets here. If you remember the diagram we had, there are 2 pitch generators now. So there's one on this row, and there's one on this row. And I've decided to call the first one the melody generator and the second one the transposition. But basically, this is just to simplify the way that I think about how this whole thing is built up. Again, we have the scale selection up here. We have the trigger probability, and we have a new slider here for clock division. This allows us to control the speed of our sequencer in a really, yeah, low granularity way, but it's actually definitely good enough for producing nice results. So we keep the clock rate of the sequencer thread, the rescheduling at the same rate, and we're just controlling the tempo with this clock divider. An additional function here, which we haven't seen yet, is the pitch range for some of the pitch generator types. So if I click play again, you will hear and also see on the console output there that the notes come from within this C3 to C5 range, and then they're either not transposed at all or transposed up by 12 semitones. So changing this range back to 0 and resetting things, you'll see that indeed this ramp that we're generating is kind of a rising sawtooth LFO, if you will. It will result in this repeating upward melody. And here we have this square LFO, which is not doing anything right now because the range is 0, but if I turn that back up to 12, then we have the rising melody, which is then transposed up 1 octave with half the speed as the melody. The really fun stuff starts when we start messing around with the cycle length, so the length of time that it takes for the ramp, for example, to get from the minimum value to the maximum. So changing that to 96 and maybe changing the transposition. And also tweaking the scale here. With a bit less repetitive melodies, especially if we start introducing some trigger probability here. And we can always switch the generator to random, the melody generator, which disables the cycle length because that doesn't make sense in the case of random. And we're going to generate notes within this range, which will again be transposed output of the pitch generator on the bottom here. We can also change that to a ramp and play around with different settings. It's really just a playground for exploring and seeing what kind of results you come up with. So let's see what kind of additional code we had to write to add all of this functionality. Again, I will start inside the sequencer. A lot more fields in the sequencer configuration, because we need to pass on the minimum and maximum pitch of the melody, which pitch generator type we're using for the melody or for the transposition, trigger probability, clock divider, quantizer. So a lot more state to keep track of, but it's all in the interest of providing a bit more control over the internals of our generative sequencer. Everything else here in the constructor is pretty much the same. So I'll skip over that. There is a little bit more code here because now we need to differentiate between the different types of pitch generator modules. But again, fairly straightforward. If we scroll further down, you'll see that the sequencer thread itself is basically unchanged. So all of the ticking, all of the processing of incoming commands, and the playing of MIDI notes follows the same structure, and it's actually the exact same code. If we take a brief look at the modules, there's a few more available now. If I scroll a little bit more, yep, there it is. So we have the ramp pitch generator in addition to the random one, which will just generate a rising ramp, which will reset after a given number of clock ticks. Again, in the tick function, we do some processing. We keep track of internal states via this counter, which counts how many ticks have elapsed. And when it is time for the counter to be reset and the ramp to start rising again, then we do that and emit the appropriate MIDI note at the end. Very similar for the square pitch generator. It has a cycle length, which determines how long the square wave will go on for, and keep track of it using the internal counter. All the rest here, the pitch quantizer and the random pitch generator are the same. And we've also added this functionality, the pitch adder, which lets us do the transposition. This one has a left and right side, basically two inputs, and on every clock tick, it gets the pitch from both of them and adds them. There's a really nice operator overriding here for the letter octave type that allows me to just do the plus and return the results. And finally, on the main file here, I will spare you the details of all the additional widget creation. It's pretty much the same logic. You create a slightly more sophisticated layout. So you might remember that this hierarchy of canvases was a bit different in the first example. So all we did was basically 2 rows and 2 columns in the first one, whereas here there are 1, 2, 3, 4 rows and 3 columns in some of them. So this is to make space for the pitch generator type, the range, and the cycle length in the pitch generator rows, and also the 2 big buttons at the bottom. So, like I said, plenty of code here, which is the case for any UI framework. Basically, the more widgets you have, the more boilerplate you need to go through. This is no exception here. But the overall logic is the same. Inside of the update function, we draw all of our widgets, we update their state based on the model, and register the code blocks that will react to changes in the UI. And I think this concludes the code part. So switching back to the slides, just for a moment. As I promised, there are some useful resources where you can learn more about the framework. Of course, the go-to place is the nannou.cc website. It links to the documentation. There's a pretty good guide for getting started. I've covered many aspects of the guide, but there's definitely a lot more depth in the actual API documentation, so I encourage everyone to check that out. And if you're interested in more conference talks that make use of Nannou, these two are the ones that I recommend. So the first one is Creative Rust by Lisa Passing, and the second one is Nannou Creative Coding with Rust, which was actually given by the artist whose animation we saw earlier on the slides. And finally, the code, the version 2, the fully featured one is already available on my GitHub profile, so people interested in a deeper dive can take a look there. And if you would like to get in touch with me, the best way to do that is on Twitter. My Twitter handle is @ZSDorak.
What was the most challenging or difficult part of building this for you?
I think the most challenging part had nothing to do with Nannou, actually. It was figuring out the whole logic of the sequencer thread and how I'm going to pass data back and forth, and to schedule it in a way that allows for more or less precise timing. Yeah, definitely that was the most challenging bit.
Hi, thanks for the talk. So I was wondering if you could comment a little bit more about your experience with learning Rust, and how long did it take to start to feel comfortable with it? And are you still fighting the borrow checker? Like what type of,
Yeah, so I think I've been learning and using Rust for roughly 4 or 5 months now. And as someone coming from more of a Java and Scala background and less from C++, I'm sure my experience and my preconceptions might be different from people who are coming from C++. But yeah, definitely there was a good 1 month initial steep learning curve where I just needed to wrap my head around the borrow checker, understanding pointers and references. They are a bit easier to understand than C++ based on my limited experience with C++. And as I said, the compiler actually gives very good error messages that help you figure those out. But as someone coming from garbage collected languages and platforms, that was definitely the biggest challenge for me. But once I got past that and I understood that, I think the different tutorials available online and the Rust book itself was really extremely helpful, and I just took it from there.
And we've got one question from Parashar, who's online. Do you believe we might soon have Rust bindings or wrappers for essential SDKs like VST, libav, etc.? Or is it more realistic to presume that we'll have an entirely separate ecosystem for Rust developers for the foreseeable future?
Good question. I have not tried to write a VST plugin yet in Rust, but I do know that some plugins already do exist. I'm just not sure about the specific libraries or the bindings that they have used. So I cannot comment on that in depth, but I know that it is currently possible. And hopefully, as more people start getting interested in Rust from the audio community, there might be a few more contributors.
Hi, I'm using a bit Rust also for audio, and regarding this question, for the learning coming from a C++ background, I'd say to get the most of the language, not necessarily the most difficult part, but I'd say if you really work on it, it would not take more than a few weeks. I'd say 1 or 2 to get really the most important part of the language. concerning the different frameworks and so on, the community is really evolving super quickly. It evolves a lot. There are many trackers online to see which projects are evolving at which pace, at which speed. There are a lot of them evolving OS frameworks, SDK. Also, I know there is a dedicated Rust audio Discord online, which is super helpful. So if some people want to get some information about that, I'd suggest you get to try to find the Discord. People are really helpful out there.
Yes, definitely. Lots of online communities within the Rust ecosystem. So yeah, definitely worth checking them out.